Nick Porthouse. This is Tim Squires. Together we want to tell you about the Equal Expert Space Agency and what we've been doing to break the world record for the highest horizontal flight of an unmanned aircraft, which is quite a mouthful. So let's start where we began. So a couple of years ago, Tim wanted to do something really cool with the scout group that he runs in Yorkshire in the UK. So he thought, well, let's get a weather balloon together, put a box of tricks, videos, sensors, various other things to get some good footage and get some data, and launch that up with the scout group. We were working together at the time, and he said, do you want to come along and give us a hand? So I went along with my kids, and together we launched a balloon up there, and it was one of the coolest things I've ever done. There's no feeling, until you've done it, there's no feeling like chasing a drone across the country, or not a drone, sorry, chasing something that you've launched into space across the country while trying to figure out where it is on the GPS and where it might come down and going the wrong way and then coming back again. It was awesome. And then realizing and telling your kids in the car on the way back that, what are we now, kids? Rocket scientists. Yeah! You know, it's brilliant. It was absolutely brilliant. But we've got quite a lot of video footage in this talk, so you don't need to listen to us droning on all the time. So let's play a quick video of that. Thank you. I'll say one thing now. We've never had kit as good as this, which is why we can't use it. So sorry about that. That video was put together from the footage that we took while the balloon was up there. And it was put together within an hour of us getting back by Tim's son, Alex, who's a bit of a whiz for YouTube videos and stuff like that. As soon as Tim sent us that, we watched it about 100 times, just not being able to believe the footage we'd got from it. It was astounding. We didn't think it would work in the first place. But then we had to go around and show all our friends and stuff like that, so we must have watched it hundreds of times in the first week and driven around to everybody to look at that. And we thought, what should we do next? That was awesome. What can we possibly do? So Tim, being actually a professional drone pilot, came up with the idea of breaking this world record. So let's do the same thing again, but this time let's drop a fixed wing drone off it and see if we can get it to fly back and see if we can get it to break that record of the highest horizontal flight. So what did we have to do? So the first thing we had to do was teach the flight computer how to fly, really. Now, it comes, and Tim will go more into the details of how this works in a bit, but it comes as a little box, and it can do basic flight, but you need to do a load more to it as well to get it to fly properly. So these drones here, which are about that big, we had them flying around the Yorkshire Dales, teaching them how to fly and how to land and and how to do the basic maneuvers before we could start using them on a more expensive drone that we might use for the actual descent. So then we needed to test some of the other components. Now, we'd already put a lot of the sensors and the cameras up into space, as you'd just seen. But we needed a bit more information from a lot of this. We needed to be able to say, right, we know that we'll be able to use the GPS at this height. The difference in temperature up there, because the atmosphere is only 3% of what it is down here. So the difference in temperature up there, it's minus 60 outside, and it's plus 30 inside the polystyrene box that we use. And you can't dissipate that heat because there's no conductivity within, in that thin atmosphere. So we're really worried about everything overheating, and we're really worried about everything freezing. And it's when you start thinking, well, actually, we're like space scientists. This is awesome. And we also needed to test the load that we were taking up there. We needed to know how much weight we could do, because if it's too heavy, when it goes up, the balloon won't reach the height where it bursts like that, and we won't get it back. It will just float around the Earth until it comes down in some random place, probably in the ocean or somewhere else. And we'd lose all the video footage and everything because we can't beam it back. So we needed to test the load, we needed to test the various components that we were putting up there. And to give you an idea of what we're playing with, we can only launch in total 4 kilograms of weight with the balloon that we've got. That's not very much. And if you think about the drone that we're launching, it's my size. It's not my weight, but it's my size. So that's what we had to put up there. We also needed to test things on the drones, like all the equipment that would control the control surfaces for the plane, and the stuff that would release the plane as well. And we've got another short video for you here, and Tim's going to explain a little about it while we're playing it. Hopefully this will play.
So we I couldn't keep on sending balloons up, so we used the excuse to buy a giant octocopter, and it pretended it was a drone, pretended it was a balloon. We put the payload, or pretend payload, underneath it, got it to go up to a certain height, which legally we're allowed to go up to 120 meters. And we sent the drone up to that. It's all totally automated. You press a button on top and it goes up. There's no remote control. The plane or the box underneath will see that it's gone past 100 meters and it'll drop it, which means that we can test the scripts that we've written over and over again without sending up balloons. And balloons are quite expensive. They're several £100s each. It just means that we can do that. And the bonus of this, you can see this one here, we're dropping one of the prototype planes from the octocopter, or what was an octocopter. We had to change it to a quadcopter because the downdraft of the propellers was actually pushing the plane and breaking the wings. Then we decided we wanted to do it a little bit higher. This is 30 kilometres high above the city of York in North Yorkshire. We dropped a small toy plane. So all the electrics for the real drone, the real fixed wing, are inside that box. You can see the white box. We were testing the servos on the outside to make sure they don't freeze as well.
Thank you, Tim. So a little claim to fame in there. That octocopter you saw up there, that was used by the Top Gear team. I'm hoping that most of you know who Top Gear are, when they were doing a lot of their foreign filming. So the Africa special that they did, they used that octocopter to do the filming of the drone that they were using to film. So if you saw that bit, little claim to fame, we like that. Tim managed to find that on eBay and got it quite cheap. It's awesome. So another big thing, we want our drone to come back. We don't want to lose it. So we need to make sure that we can launch it and then it'll go off on quite a long trip and then come back to us. So after we'd got the basics of the flight computer working, we then had to reprogram it to do a load of other stuff about coming back to us and doing it itself. We can't remote control this. It's miles and miles away. There's no way we can control it in real time. And if we can't control it, then if something happens, then we lose the drone. So what it needs to do is do all of this stuff itself. So it's totally automated. And Tim will go into a little bit more of that now with this video.
So this video... and it worked perfectly. So I'm really glad with that test.
Thank you. I'll just say, when Tim said he sped after it, what he means is he obeyed all traffic laws and calmly and carefully went after to find out where it was. Just put that in there for any officials in the room. So part of what Tim was saying there about basically the drone just aborting when it has a problem. We need to put a lot of work into emergency procedures. There's no way we'd be allowed to do this if we didn't have things like the drone. If another aircraft comes into the drone space, the drone needs to give way. The drone has no priority at all. We don't want to be responsible for bringing down an airliner or anything like that. So it needs to check that that's there. It needs to be looking for things like electricity pylons or trees or anything like that, so that it can just itself move out the way. Again, we can't control this while it's flying. We also, for part of the safety case, which we'll come on to in a bit, we need to have emergency landing sites mapped out. So we need to be able to program the drone to be able to land in one of these sites if it has a problem, or if there's a real catastrophic problem like a loss of power or something else, it shuts down safely and just crash lands somewhere unpopulated. So all of that needs to be done as well. So we've done all of that. Everything was ready probably over a year ago now, and we've been ready to do the record attempt for all that time. During that period, we were talking to the UK Civil Aviation Authority, who were really excited about what they were doing. Tim was constantly updating them with stuff, and they were saying, oh yeah, this sounds cool. And then after a year of talking to them, they went, no, you can't do that. Now, we can understand their decision. Their job is to keep everybody safe. They're meant to be there to make sure that we don't bring down an airliner, or we don't crash into somebody's house or car, or land on a road or something like that. So we definitely understand the decision. We just wish it hadn't taken a year, because that would have given us time to look at other options. They were saying, we love this idea, it's great, and then said no, which was a bit frustrating, really. However, where are we now? So, we're in Pune. Awesome. Thank you very much for having us. It's been great coming over here and seeing a bit of India. We've loved it. But where are we with the drone? So we can't launch in the UK, as I've just said. But what we're doing is we're getting a professional safety case writer to put a safety case together for us, which might allow us to launch in the UK if that comes back favourably. We're getting professional training, which will help the safety case. And we're continuing the test. So that test in the Scottish Highlands that Tim was just showing, that was something that was done quite recently. And every time we test stuff, we find better ways of doing stuff and improve everything we're doing. And recently, we were talking to the Civil Aviation Authority in Iceland, and they're quite excited about it. But they've said from the beginning, we need a safety case there. Now, as part of the safety case, you need to understand where your launch sites might be, and where your landing sites might be, and where your emergency landing sites might be. So how are we going to do that? Well, we had to go to Iceland. What a shame. And here's a bit of a video about our trip around Iceland.
stop now, it's going to erupt. You ready?
Yeah.
I don't know if you heard what I said at the end of that video. I've been standing there for about 10 minutes on my phone waiting for the geyser to erupt. And I said to Nick, if I press stop now, it's going to erupt. So, yes, Iceland. Why Iceland? Well, because they'll let us do it, probably. But it's very close to the UK. It takes a couple of hours to fly there. And also, it's got the bonus of 24-hour sunlight. Well, one of the stipulations of the safety case is that we have to take off after 8 o'clock at night when most of the tourist planes have stopped flying. The low-level planes are not allowed to fly at that time of night. So we've got to land before sunset, which is great because if the sun doesn't set, it means we've got forever. Well, 6 months at least. Realistically, it's going to take about 2.5 hours for the mission, which means if we take off at 8 o'clock dead on, then it means we're going to be finished by about 10:30, 11 o'clock if nothing goes wrong, and everybody will be happy and it'll still be sunny, which means we can actually see what we're doing. What we've got is we've travelled the whole of Iceland. We've planned the mission extensively to say where we're going to go. First of all, this is what Iceland looks like, because just in case it's a bit further away from the UK than we live. We planned it extensively. What we did was we mapped out 2 days of travelling to go and see as many sites as we possibly can in 2 days. So poor old Nick had to drive for 9 hours on one day. And we stopped, we got out for 30 seconds, took some pictures, did some recordings of each place, and then which ended up looking like this. So we got a whole load of data from each recording site. We ended up with 2 launch sites, 2 potential launch sites. Both of them are on black beach type sand, which will look amazing on the video, I hope. There was a little bit in that video there. And then we got one landing site, one primary landing site, which is a scout centre. The scouts have kindly said that we can use any of their land in the whole world, which is great. We're insured for it, and they'll clear the area for it. This one is, I'm not even going to try and pronounce it, in Iceland, right in the centre of Iceland. It's great. It's got an emergency lake next to it, so if we wanted to ditch the plane right at the end, we can ditch it in the lake and go and get it with one of the scout canoes. If not, it's got a giant field that we can land in, and a nice empty area around it as well. There'll be lots of people there, so lots of people watching. I'm going to do a little bit geeky bit now, so for all the geeks in the room, you're welcome to go to sleep. The inside of the plane looks a little bit like this. This was taken over a year ago, so it looks a little bit more complicated than this. The whole thing is based on a flight computer called the Pixhawk. If anybody wants to come and have a look at it, it's up here. So it was brought out. The original version was brought out about 4 or 5 years ago, and they brought out the Pixhawk 2 November 2017, and that's actually what makes this whole mission possible. There's lots of people have been trying to do exactly the same as this mission since the 1970s, and nobody's actually managed yet. Usually what they try and control it from a remote control. When it's 30 kilometers high, the latency on the remote control is too much. Half a second is far too much when you're traveling at hundreds of miles an hour in a very thin atmosphere. So by the time they've actually got the plane, by the time they've tried to correct the attitude of the plane, it's already gone all the way over, and then they overcorrect and it goes all the other way. We have a friend in the States, in Texas, who's helping us with the project. Monroe King III, he's a professor at Texas University. He's a proper rocket scientist. For his living, he designs rockets. He's tried this 7 times. 4 times they couldn't rescue any of the plane. It can be completely destroyed on landing. 3 times they actually managed to get the plane back and a little bit of footage, but it only actually started flying below about 5 kilometers high. So just got normal footage back. You couldn't really see what it was like. The flight computer. So we have the flight computer. Inside this flight computer, there's 3 IMUs, inertial measurement units, so it can tell which way it's facing, with real-time software inside that to correct the plane's attitude. It has a compass. It actually has 3 compasses because it's got 2 external ones as well. There's 2 power sources, one for the one that controls the flight computer, and the motor, and one emergency one that will just control the flight computer and the ailerons when it's landing. So just in case there's not enough power for running the motor, it will glide back down again. We have Wi-Fi. Now, Wi-Fi doesn't sound much, 30 meters, we're going 30 kilometers high. But instead of taking the plane to bits to get hold of the inside, you can just connect to it on the ground. We can do changes in tests and so on. So Wi-Fi is actually really useful. And inside it has a companion computer. It's like a Raspberry Pi. It's called an Intel Edison. It's very similar to the Raspberry Pi in the fact that it runs Linux. There's a Python script on it. I'll do a little bit on the Python script later on, but if anybody wants to help us with that, I had a nice session with the Pune guys yesterday. But it is open source, and if anybody wants to help, please, need your help. I'm now a technical architect, so I don't really touch keyboards anymore. So running real-time software up into space above people's heads, I do need some help, please. There's some really accurate GPSs plugged into this, 2 of them. They're called the HERE GPSs, and they go down to a centimetre accuracy, several centimetres accuracy, which means that landing is a lot easier. Automated landings, they're great, but GPS is only accurate usually to about 10 metres. You can imagine if you're trying to land on the ground and the flight computer thinks it's trying to land 10 metres underground, it doesn't make for a very graceful landing, which I found several times. There was a picture earlier on of one of my landing attempts, and the wings came off and the flight computer came out and damaged. We're on now prototype number 4. Three of the prototypes were damaged on automated landing, and one of them was damaged because I put a 2 in instead of a 20, and it crashed into a wall. To stop the plane hitting other planes, we have something called ADS-B, which is a worldwide standard. What it does is if anybody's been to, what's the website where you can track planes? Anybody know the website where you can track planes? Flight Radar, that's it. So Flight Radar uses the input from something called ADS-B, which now you can get them. A few years ago, when I was doing paragliding, they were trying to get all paragliders to have an ADS-B transponder. And at the time, it was 1.5 kilograms. Now, when you're paragliding, 1.5 kilograms is a lot. Nowadays, they're smaller than a credit card, half a credit card, and that's all you need now for an ADS-B. The plane can be detected 10 miles away, so about 17 kilometers, and it can also detect planes coming its way. And it can detect if it's the flight computer can detect if the paths are going to cross. So it will recalculate its flight. When the other plane's gone past, it will come back onto its flight plan again, which is absolutely amazing to watch when you're doing it low level. A jet will go over. You say, I want to have a 10-kilometer separation just for testing, and the plane will drive over to the other side of the field, and then it will come back again. It's only a small test, but it's quite thrilling to watch it fly itself and calculate it all itself. And it also appears on radar, so it will appear on the air traffic control radar. It has a very sensitive airspeed sensor on it as well. That won't work above about 5 kilometers high, so it has to rely on GPS, but the airspeed sensor is very useful for the automated landing. Camera payload. So it has. We're going to send up 3 cameras. We've sent up all these cameras before, and they worked. One day was a bit cloudy, and as it went through the cloud, it's got a bit moist, and the actual moisture froze. So the third time we sent up, we didn't actually get very good footage because we just got ice. But hopefully, when we do it in Iceland or wherever we do it again, we'll do it on a clear day and make sure that the ice doesn't freeze on it. So there's a Hero 5 session, which we tested for 4.5 hours. It got a bit warm, but it worked well. Samsung Gear 360, which is amazing to watch. I run a scout group, and we got the scouts to bring all their mobile phones in and put the YouTube video of, there's a YouTube playlist on the Equal Experts, by the way, if you want to watch any of these, of the balloon going up with the 360 on. And there was 30-something scouts in the room with all the goggles on, and you could tell the point where the balloon burst and it started falling again because almost all the scouts fell over. We're also going to have a box above the drone. So we want to see it fall. It's not just because it's really cool footage, but because we want to know how it falls. In 3% of atmosphere, it's probably just going to fall similar to this. So we're pointing the nose straight down so that it accelerates down to about, using gravity, it's going to accelerate down to about 80 or 90 meters per second, which on the back of a piece of paper we've calculated is absolutely perfect for the first try of horizontal flight. You can see from this, we tried putting the camera inside a case. One of the cameras we sent up on one of the tests was a gimbal camera off the bottom of an Inspire, DJI Inspire drone. It worked really well. The camera stayed really still. Most of the videos on YouTube of these balloon launches make you feel sick when you're trying to watch them. So we sent up a gimbaled camera, and it worked really well. Unfortunately, because of the ice on the outside of this dome, all you could see was extra stars going around like this, which spoiled the footage. But it was a good try anyway. The script. All right. So the script is the most important bit of the whole thing. It's the hardest thing to program, and it's the hardest thing to test as well. Even with the octocopter lifting the plane up, the script, we can't really test it because it adjusts all the parameters for the plane depending on the height. We haven't got a low-pressure environment to test it in, so we're trying to simulate it. As I went through with some of the Pune guys yesterday, the simulator doesn't work well above about 2 kilometers. So it still thinks that the air pressure is 100% at 30 kilometers high, so we can't really test that. It also, the simulator expects you not to be stupid and drop a plane from a cliff or a balloon. Expects it to take off from the ground and land in the same place. So the simulator software needs a little bit of tweaking so we can test it properly. The safety case, it's important because the safety case needs to know that the software has all been tested and it's all working. So we had a few features that we found. Other people call them bugs, but features. One of them was when the hardware was first released, the Pixhawk 2 was first released. This is Pixhawk 1, but all the 2s are stuck in the planes, which we couldn't get through customs, unfortunately. But the Pixhawk 2, when it was first released, had a small bug in it where if you put too much power through it, it would short out and then stop flying the plane, which was quite embarrassing when you're trying to show people how well you've programmed this plane, and then suddenly it would fall out of the sky. It only happened once. The airspeed sensor is extremely accurate, but if you're putting it in the back of a small car, then it does bend, but you can't see it if it's bent. Just 1 degree makes a huge amount of difference to the quality of the reading. So when it comes into land or you're trying to chase it with a drone and take some film, it's very difficult to keep it at a steady speed when the airspeed sensor is bent, as I found out. Tuning took ages. It's got auto-tune on it, but every time you move the camera around, take the battery out, put the battery back in again, if you move the battery backwards and forwards by a millimetre or two, changes the centre of gravity. So you then have to auto-tune it again. So I've set it now so there's places for the battery to go. There's different mount points and different tuning settings for each place where I put it. Dogs. In Yorkshire, just about everybody has a dog. Now, dogs have an uncanny ability to go and sit and watch you film. So someone else will come along, they'll be walking along the moorside, top of the hill. There'll be nobody else there, but you'll find this dog runs away from its owner and will sit exactly where the plane is programmed to land. They're just, I don't know how they do it, if they have radar, or it's just amazing how they are. Wing wobble. So you've got these quite long wings, and they're made of foam. They're made of the white foam EPO. And when they get to really high speeds, they actually start to oscillate, which means that they can break apart. And at 80 meters per second, they're designed to fly at about 10 to 15 meters per second. But up in the high atmosphere where it's thin, we're going to 80 meters per second, 80 or 90, and then we'll slow down by actually trying to fly horizontally. If the wings start to oscillate at that sort of flight, then we'll lose the whole plane. And it's something that other people that have done the same thing have found. So we're just keeping it in mind, because we can't really test it at 80 meters per second down on the ground. It will just tear itself to bits. Weather forecasts. Weather forecasts are really, really accurate to about the hour, unless, of course, you're stood on top of a hill. I remember showing my kids, as we were trying to launch the plane, this is the weather forecast on my phone, and it said sunny with cloudy periods, but we couldn't actually see the weather forecast because it was covered in rain and snow. Servo motor freeze. It's one of the things I didn't really think about. The grease in the servos, in the little motors that control the surfaces, they all have a specialist greased in that actually goes down to minus 31, but it freezes solid at minus 60. So what we have to do is you have to keep them moving. Then you have the opposite problem. There's no air there to conduct all the heat away, so you're moving the servos backwards and forwards to keep them warm, but then they can get over warm. But you haven't got a temperature gauge on the servo, so We've done some more super duper calculations on a tiny piece of paper and said we think that if we move them backwards and forwards every half a second, they should stay warm enough, but not too warm, to actually be ejected. And you saw the video there with the box with the servos on the outside. That was testing them with different greases to find out which one's the best one. It seems to work really well. We didn't have any problem with the 4 servos we sent up. Hardware delivery. These things come from all over the world. So this comes from where does it come from? India, I think. No, one of the actual planes comes from India. This comes from America. The GPS comes from Australia. And you can order them all, and they come within 6 weeks of each other. But when you've got one part, it's really annoying when you've got one teeny tiny bit missing, and have to get it through customs. VTail design. What we did was we designed it to be a delta wing. I don't know if anybody knows what a delta wing. It just looks like a triangle. That's what we thought would be the best one to set up. It's the simplest design. It's got the least moving parts. But when we discussed it with Professor Monroe King III in Texas, he said you need a really long tail, and preferably an inverted V-tail. I haven't questioned him. He sent me all the maths to do with it, but it does make sense to have a long tail when it's no atmosphere, so you get more control, and the tail means that you don't have to worry so much about centre of balance. Aerial footage. Now, aerial footage technically in the UK and most places in the world is illegal to use unless you have an exemption to film in the air. Luckily, when this footage was all made, I had an exemption from the CAA, but if we were to film anywhere else, we have to get exemptions from everywhere else, and it's quite a long process to do exemptions, even if you've done it in another country. So this is a little bit of a video of some of the features that we've had. Right. I'm currently up a tree trying to work out how I get down without throwing the plane down. It was right at the top up there, and I managed to get it to there without too much damage. But we'll see. Right, here we go. If I don't speak to you again, it was fun. So we've there's the software, both the software that's in here, which is in C, and the Python that runs on the companion computer, both open source. If anybody would like to help, please get in touch with us or have a look at the GitHub project. It's got a README in it, which I need to bring up to date after showing the guys yesterday. But if anybody wants to help, it would be absolutely fantastic if you'd help. So we're hoping to run the project over here as well. Launch over here eventually, and it'd be really nice to have as many people involved in it as we can.
Okay, so we've had a long time to think about this. What else can we do? If we get this launch done or not, it'd be really nice to be able to finish this off. But what else can we do with the stuff that we've already been looking at? So there's a challenge over in Australia called the UAB Medical Challenge, which is to do with using drones to help stranded or injured people in the outback. Obviously, it's a very remote area, so it's very difficult to, one, find people, and two, get any information about their status or anything like that. So the idea is that you use a drone to go out into the outback and pick something up from them and then fly back. And it all needs to be autonomous because, again, it's too far away to use a control. So we entered this last year and got through the first round. They were quite excited by what we were doing, but we just didn't have time to take it through to the second round. However, we want to do that, so we're going to submit again next year for 2020 for that one. And Bethan's going to give us a hand with that. She's running EcoExperts Australia, so hopefully we can do something over there. Very similar is the Lake Victoria Challenge in Africa. They're trying to do a very similar thing about finding or helping stranded people. And looking at how we can deliver medical supplies or something like that to people who are out in remote areas. That's next June, and we're hoping to get ourselves entered for that as well. There's a lot of stuff around water, about drones on water. So if you can remove some of the people from a lot of the shipping that goes on, that could be, that could be really advantageous in terms of saving money or saving lives. So there's various races that go on around the world using autonomous drones to see how far or to see whether people can arrive at a predetermined place. And there's a lot of scientific underwater exploration going on. We still know less about the bottom of the sea than we do about a lot of the planets in the solar system, but that's improving quite a bit. There's a lot of footage on TV about remote drones, very expensive remote drones, being sent down to great depths. But they're hugely expensive. None of us could afford one of those, unless you're very rich. But what if we could use commodity hardware, like we're doing with the planes, using the same sort of software that we've built for the planes to do this sort of stuff? So that's something that a few of our associates are very interested in. And then there's things like fixed-wing swarms, which very few people are doing at the minute. So if you wanted to map out a large area, using one drone would take a long time. But if you could get 50 drones all to communicate together and map that area very efficiently, then that would save a lot of money and a lot of time. Or maybe you're searching for somebody who's lost and you want to use it for search and rescue, then you could use a large number of drones, very cheap drones, to go and search that area, much quicker and cheaper than using helicopters or single drones or anything like that. So there's a lot of ideas that we've got, but we're really interested in what ideas other people have. And if you've got any ideas at all, please get in touch with us. We're open to investigating anything and seeing what can be done. So, nearly at the end, but there's some thanks that we want to give out. First of all, thanks to EcoExperts. A little bit of a story here. So we said at the beginning that we launched that original balloon. Tim paid for all of that, and with the Scouts' help. But then when we thought, we want to do this bigger thing, we realised it was going to cost us a lot more money, and it was probably out of our price range. So we spent about a week putting together a business case, thinking about all the stuff we'd need to buy, and then I took that to John Dickinson, who's pictured there, who's now our co-CEO, and played him the video, and he didn't even look at the business case. He just went, "Hell yes, we've got to do that. That's really cool." So he took that to our then CEO, who went, "Hell yes, we've got to do that. That's really cool." And they gave us twice the amount of money that we were asking for to do it. Which was brilliant because we spent and then went back and asked for the same amount again, which they gave us, which was brilliant, and we've spent quite a lot of that as well. But hopefully we're near the end of that spending, and we're nearly at the point where we can. We are at the point where we can launch, but we just need to get the permission somewhere. So EcoExperts have been incredibly helpful and supportive with everything we're doing. On there we've got John Attaway, who is our head of content. He's been doing loads of blogging about the space plane. Lauren McDonnell designed these t-shirts, bit of modelling, and she's designed hoodies for us, and she did a lot of the graphics that are on this presentation, so she's been really, really helpful with that. Kathleen Collier, who's our head of marketing and comms, she's been getting everything sorted for us and delegating to other people to do this for Nick and Tim. This is awesome. So it's been really good. And Constance Smith we've got in there as well. We've given her the honorary title, as we've given ourselves titles for ESA as well, of Director of Communications, because she came along to help us when we were trying to get in touch with other countries to find out if their aviation authorities would allow us to launch. And she really pushed people like the Iceland Aviation Authority and helped us with those comms. So that was really, really good. Can't fault EcoExperts. They're an amazing company. I joined them as a contractor about 4 years ago and went permanent about 2 years ago. And I wouldn't have done that if I ever wanted to work anywhere else. They're just brilliant. So a couple of other thanks very quickly. So the Addingham Scouts, Tim's Scout Group, because we're part of them, they pay for all the insurance, which is quite expensive, which is very nice. But also they've given us a load of help in terms of what I help with as well, which is basic labour on the site. Tim does all the engineering, all the software. I do the admin and the labour. But then when we get the Scouts to help out, it relieves my job a little bit there. and Munro Lee King Jr. III, who's the rocket scientist that Tim's mentioned a couple of times. He's been really, really helpful in designing the plane and giving us ideas about what might work, given that he's done this a number of times himself. So I want to leave you now with just the last video, but this is a little timeline of what we've done. Tim put this together yesterday, the day before, and I love it. It almost made me cry, to be honest, but I am quite close to this, so and I was very tired after the plane. So I'll leave you with this video.
There is something in the air, like I have to go nowhere. If someone ever asks me, I can never say where I'll be. And people say that someday I will lose my mind. They're always wondering why is a waste of time. I am trying to figure why in my heart I still feel fire. Anything that has been done to fix it, or why it takes so long, 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 so long. Feel the light, oh, shine so bright, let it shine. Feel the light, oh, shine so bright, let it shine. Peace of mind is ruled by fear. We almost found the elixir. And people say that someday you will lose your mind. They're always wondering why is a waste of time. You don't have to figure why in your heart you still feel fire to forget things that now are gone. You don't know, but it won't take so long. It won't take so long. It won't take so long. It won't take so long, so long. Feel the light, oh, shine so bright, let it shine. Feel the light, oh, shine so bright, let it shine.
Thank you, guys.
You guys mentioned that you were collecting, you had 3 or 4 camera modules on the flight, which is collecting, height data and other kind of space curvature and so my question is related to, like video data is difficult to get actual data points from. So what other kinds of data did you collect and what other kinds of sensors did you use to get those data?
We've got on the balloon missions we had what was known as a black box, and it had barometer measure, so pressure measure, had internal temperature, external temperature. Each of the images was also stamped with the GPS from the flight computer. So not the video, but each of the JPEGs that were taken. We had one of the cameras was taking stills every 1 second. Yeah, those have got not hugely accurate because when you get above, is it 10 kilometers? If you have GPS accurate, very GPS accurate, it's actually counted as weaponized. So we try not to do that. So everything's stamped with that. But if we can, the end product of this hopefully will be a stable, cheap platform that we can send up regularly with a down-facing camera and take regular pictures. We're hoping then to get an exemption so we can take very accurate RTK-based pictures which are centimetre accurate. We can also record the telemetry, so we know we also recorded the telemetry, so we knew which way each of the cameras was facing. So we can stitch them all together and make it so that it's one photo mosaic.
Anything about the height data? Like
Yes, we have GPS and barometer, so we have accurate height data. Well, height data accurate to about 8 meters accuracy, up to 10 or 12,000 meters, and then above that it's accurate to 100 meters. The first balloon got up to 36 and a bit kilometers. The second balloon 34, but that's only because it had a much bigger payload. The third balloon, which is the one that dropped the toy plane, that dropped the toy plane very, very accurately within 100 meters of 30 kilometers high, and then the balloon continued to 32.5, I think, maybe 33. So is that what you mean?
Thank you.
Any more questions?
So I looked this up when we started doing these presentations, and it was around, so there were different ones. So the private record was about 18,000 meters. To give you an idea of scale, so your commercial jets, your jumbos and stuff like that, they fly at about 10,000 meters. So we're more than 3 times higher than that. So yeah, the private record was about 18 kilometers. And then NASA's record was something like 25,000 kilometers. So we had potentially 5,000 kilometers in there.
29, wasn't it?
Yeah, but NASA has done another one since, so it's now around 29. So we're dropping at 30, so we've still got a chance of beating NASA there. But they've got a little bit more money than us, just a little. And they've got some cleverer people too. But even so, if we beat, if we can do it at 20,000, that's the highest private one, and it'd still be a world record for that. So yeah, that's what we're looking to do. I mean, one of the things, and Tim mentioned it earlier, is that we'll drop the plane from 30,000 meters, and it will continually try to level out. And if it fails, because the pressure's not enough, it's not getting enough lift, then it'll fall a bit longer, get some speed back, and then try again. And it'll keep on doing that. So it's not like we've got to go down to a specific height and just try there. There'll be loads and loads of attempts to do it. So hopefully one of those will succeed. Oh, and I just wanted to point out, so for those of you like me who can't work out what 80 meters per second is in miles per hour, it's about 500 miles an hour.
Just under.
Yeah, just under 500 miles an hour. It's pretty fast.
Anybody else?
Any more? If you want to ask us questions later, we're going to be around all day, so just come and see us. Thank you, guys.